of threshold gates. Threshold gate is a function, is a Boolean function of this form. Where
weighted majority. Just weighted majority, yeah?
Yes, just a sign of linear combination of Boolean variables with weights. W's and t are integers, and W's are called weights, and T is a threshold. One important threshold gate is a Boolean function. One important parameter of threshold gate is its weight. Its weight is a maximal absolute value of Ws and Ws and T. It is interesting to understand what constraints can be put on this value. It appears that this value should not, that we don't need too high weight. It's the theorem. Let us denote by T the set of all threshold gates. If some function is computable by some T from T, when it is computable by T1 and T1 has weight n to the power of n.
Volodya, write the implication sign from the premise to the... Okay.
So if you can separate some vertices of Boolean cube by any hyperplane, you can just shift it a bit, making the coefficients of reasonable size without crossing anything.
Yes. This is what you say now. This is a result of moreover. And it appears that, in fact, this bound is tight. That is, there exists a function such that f is computable by T from there. And every threshold gated compute step has a weight of size computable by T. T power of f. And there is a natural generalization of threshold gate, namely perceptron. Perceptron is a Boolean function of such this form. The sign of combination of functions depending on input variables. Not double that. W's and the W's and T are still integers, and F's it's a Boolean function dependent on at most the variables, d variables. Perceptron of order for every natural d, there is a definition. There is a different definition. Depends on d variables.
If I is a Boolean function, yeah?
Not more.
Yeah.
F is a Boolean function, yes.
Yeah, yeah.
Dependent on not more than on at most d variables.
So perceptrons of order 1 are just
threshold gates, yes. The upper bound on weight of a perceptron is still maximal absolute value of these integers. The upper bound is can be translated to the perceptron rather easily, and so if some function f is some function f is computable by a perceptron of order d, then it can be computed by perceptron of order d with weight n to the power of n to the d. And it appears...
And as now the number of variables, yeah?
Yes.
And not the number of functions.
Yes, n is a number of...
But it depends on I, right? N depends on I.
No, it doesn't depend. Here are all Boolean variables, but fi doesn't depend on all of them. It depends only on d.
Yeah, but the number of functions...
Just for simplicity of
Number of functions is k.
It's n to the d, yeah?
Why?
at most.
At most.
most.
So we have no specific bound for we can allow. It's not bounded separately.
So actually, you can just write there k equal to n to the d to stop the discussion.
Why n to the d?
We write most
2 to the n to the
2 to the n to the d.
No, no, no. 2 to n d.
2 to n d.
There are a lot of Boolean.
Probably k is more simple.
Okay. To stop the discussion. Like, okay. Good.
No.
No, I want to.
I would say
But it's not important for the
Yeah, I would
present
say
talk how many functions we...
No, because if we try to estimate if we try to see the separating plane, the dimension of the space where the plane happens is k. So if k is large, it could happen. It's not. It's a big surprise that the bound doesn't depend on k. So that's why I'm asking.
Because k is bounded by some function of n and d.
A very large function.
Okay.
You have only
Polynomial.
Why? But
now you wrote something like 2 to the n, 2 to the n.
very exponential.
No,
2 to the d.
There are well, not at most this number of functions. This is to
choose d variables.
To choose the variables, and this to
Choose a function.
Yeah, and this O constant may depend on d.
yes, this constant is depends on d. And it appears that this bound is type 2, like in the previous case.
It would be nice that it is symmetric to half the
Or also you can close it, it's not a raise.
There is a function.
And you should write also some symmetric to the what's in brackets. Right?
You mean from the right to the left?
No, yeah. If there is an author of that theorem, there should be the author of that one too.
Yeah, okay, but we guess.
Yeah, we guess. Okay. Don't try.
I will use a large letter for a function f for some reasons. But there exists a function f that is computable. F is computable by a perceptron. And for all perceptrons with compute
Of order d.
of order d, yes. Order for all d. And for all perceptrons of order d that computes f, they have all such perceptrons have weights order n to the power of n to the that is the result. And now we are going to define the function that is that was mentioned in this theorem. It is not a standard function, some well-known function, so it will be not very easy. And we started by defining a function that was from theorem of Hospital.
Yeah, but this is quite explicit function. You
Yes,
don't rely on
this is explicit function, and you're right. Big letter.
It's just to confuse, I guess.
Okay. Let us consider that this function would be from. At first, it would be convenient to switch to the -1 Boolean variables. X is it doesn't it is not important for formulations of the theorem, but it is useful for defining a function. Function f would be from n bit terms, and let us consider let n be the power of 2. And let us consider input of function f as a function. As a function f from empty strings. Here is m. In the following way. The input of function f is just the list of all values of function f small.
True statement. Yeah, the true statement.
Yes. Now we need some definitions. Let us denote the set of all all natural numbers from 1 to m by this thing. Now we need some functions. Phi for all subset of this set. We will define a function a monomial. In fact, it will be monomial phi alpha, and it would be just a product of all variables from the set alpha. If alpha is empty set, phi alpha is 1. Also, we need a standard inner product of two functions. Standard product, and we will look at the Fourier. Okay, these functions forms an orthogonal basis in the set of all functions on n-bit strings. It is not hard to see. And we will look at the Fourier coefficients of input function f in this basis. That is, we will look at numbers f. Now we can define almost can define function of function f would be a sign of f of scalar product of inner product of f phi alpha, where alpha is maximal such that this is non-zero. That's phi alpha is not zero, but it doesn't clear what is maximal. We need some ordering on subset of this set. And this ordering will be...
Now, before you completely rate this, maybe somebody can summarize what is happening, because Hastad is, of course, very clever, but why we should consider this function, how it arises, what's happening? Does anybody understand? Or at least just maybe somebody, for example, Koller, can repeat the definition of the function.
I can. Actually, I don't understand why we should take it. I know the proof, but I don't understand.
Yeah, but just repeat the function for stupid people again.
Okay. The argument of hosted function is considered again as a function, as Boolean function.
So we classify functions as good or bad. And this is classification is what we
Okay, in the space of all those functions, we consider the usual inner product, right?
Yeah.
Okay. Then we take the Fourier coefficients of the given functions.
Yeah.
And we take the first Fourier coefficient which is non-zero.